Hello everyone, and welcome to another live stream here on Freaky Physics. And today we have another lesson with Geeta, so Geeta's gonna be here soon. But before anything else, my kid's here and wants to say hi. Say hi.
Hello.
Say goodbye now.
Okay, bye. See you next year.
All right.
I mean, see you next year.
All right. Bye bye now.
I mean, see you in a decade.
Okay, there we go. All right, so we're still waiting for the student to come in, and for the time being, I am setting up the board. Um, well, should be in any second now. But anyway, uh, this one is copied. Right. Okay, so we're just continuing the lesson from last night or yesterday, whatever you want to call it. Um, I'm just gonna copy all the images that, well, all the problems that was sent over 2 days ago. All right, so she's here. Hi,
Hi,
Gita. Good.
how are
Good
you?
afternoon. Good. I'm good. Thank you for
Good
asking. How
afternoon.
about you?
I'm good, thank you.
Yeah. All right. So, are we gonna continue from what we were doing yesterday and just go over the problems?
Yes, that's what I thought.
All right. Okay. So get the, I'm getting the problems ready for now. Um.
Hmm.
Okay. Right. While that's getting ready. Okay. Oh, I see you sent. Okay. Never mind. Got deleted. What is
Yeah,
that?
I thought we already had too much for this lesson.
I'll just put it up there. Let's see if we can get to it. I think we should be able to, considering we have a lot of questions. Well, not that many today. Just you sent over like 5 questions in total, or
Yeah,
5 images in total. So just send it again later if we have time. Yeah.
okay.
All right. Okay. I think I'll share my screen now. Where is it? There it is. Okay. And let's go here. Okay, let's take a look at this first. The first question you sent over that I've copied was uh, not this, not this. This is the second question. Let's go to this one. I think you've sent me this question before. Okay. Um.
I'm
Okay.
not sure.
But
Maybe.
either way, let's just go through this. I think this is the one that has no solution to it. Okay. But let's go through. Let's just try to do it again. Within the next 3 minutes. Okay. So first of all, we need to look at the Hertzsprung-Russell diagram to determine a few things. Okay. But before we do, let's just label everything in here first. Um, the maximum wavelength is 580 nanometers. Now, I'm just putting these up here so it's easier to look at. Now, apparent brightness. In other words, apparent brightness would be just the brightness, right? That's going to be 8.3 times 10 to the minus 13 watts per meter squared. Okay. Now, the the problem here, and oh yeah, I think I see it now. Okay, so let's go back and just take a look at the Hertzsprung-Russell diagram. Okay, I'll get a different copy of that here. Hold on. Okay, let's take a look at the slightly different one. Okay, this one is, okay, which one looks good? I think this looks good. Okay, so we need to know, we basically need to know the luminosity of this thing in terms of the luminosity of the sun. Okay. Um. here we go. Copy this image first. Now, I think I recall from last week that since there was a slight problem, so I actually double checked everything. The problem with solving this particular problem here is, yeah, we may have a Hertzsprung-Russell diagram. We can actually determine from this Lmax, okay, we can determine from this Lmax the temperature. So from here, the temperature, if we go to the, excuse me, data booklet. Okay, so if we look at the data booklet, the formula that relates this maximum wavelength to the temperature is given by Wien's displacement law, which I will be double checking just to be sure. Wien's displacement law. There. From here, T times L max is lambda max rather would be equal to 2.9 times 10 to the minus 3 meters per meter Kelvin. Okay, so from here, we can determine. I'm just gonna shortcut this now. I'm gonna go straight up, use the calculator here. We're gonna get 2.9 exponent to negative 3, and we're gonna divide that by 580 times 10 to the minus 9. Nanometers is minus 9, right? So we're gonna get here that the temperature here is gonna be 5,000 Kelvin. That's it. So the first thing we're gonna look at now is the Hertzsprung-Russell diagram. So from here, where would the temperature 5,000 Kelvin be? It should be around here. So 5,000 Kelvin should be around here. So we're either in the main sequence, giants or supergiants. Okay. Now, we are given the brightness, and this is where the problem is difficult, becomes unsolvable. All we can get is the temperature. Okay. Because here you're given the brightness, and this apparent brightness is again as seen on Earth, right?
Yeah.
Okay. Now, I'm going to delete this part first. Now, as seen from Earth, we see this, but remember that the brightness is dependent on two things. Dependent on the luminosity and the distance. But there's where the problem lies, okay? We cannot solve a luminosity if we don't know the distance. Similarly, we cannot find the luminosity if the distance if we don't know the luminosity. And if you look here, it doesn't say anything about what the luminosity of the star actually is. It just says what the brightness is, and it just says what the luminosity of the sun is. In other words, this makes it unsolvable.
And if we found the luminosity from the graph?
We could, but here's the problem. The luminosity, we only know the temperature. We've already solved for the temperature, but we don't know where on this line, where the luminosity is for this particular star, unless it's mentioned that we are at a main sequence star. It's not mentioned, right? Now the main thing that I can really think of is if this were mentioned, we can already answer it if as main sequence. Okay, because if we look at the main sequence part of the Hertzsprung-Russell diagram, it's basically just let's take a look at the possibilities for here. Yeah, so if we go back here, I'm gonna use orange for this. If we're here on the main sequence star, we know the luminosity is gonna be 1, approximately 1 at least.
Yeah.
Okay, but that's the problem. We don't know, because it's not mentioned, whether it's a main sequence, a giant, or a supergiant.
Could we solve it as if it was 1?
Now, let's assume, if we assume that, then yes, we can solve it. Okay, so as is, we cannot solve. Okay, but let's make that assumption. Assume L equals the luminosity of the sun, right? Okay,
Yeah.
so from here, we can now solve the distance. What's basically the idea here? Let's go back to the formula. The luminosity, the brightness is equal to the luminosity divided by 4 pi times d squared. So from here, let's just solve this now. D would be equal to the square root of L over 4 pi b. That's it. We put our values in. Luminosity of the sun is given. The brightness is given. We just do the math. Okay. Again, I'll do a bit of a shortcut. I'll just put this straight in the calculator. We're gonna get luminosity is 3.8. Oops. 3.8 times 10 to the 26. Then we're gonna divide that by 4 times pi times the brightness. The brightness is given as what again? Sorry. Let's go back. 8.3 times 10 to the minus 13. 8.3, excuse me, exponent negative 13. Okay, and then we take the square root of the answer. We found the distance in meters. Okay, the answer here, D would be 6.04 times 10 to the 3, 6, 9, 12, 15, 18. 18 meters. Right? Then from here on out, we can convert to light years. We have a conversion factor. And then we also convert the light years into parsec. Okay?
Yeah.
All right. Do I need to show you how to do the conversion, or you're good?
I'm good. I think we did it like
Alright.
last
Right.
before.
Yeah, I think this is the only issue. Once we assume it's main sequence, it's easy. Okay.
Okay.
All right. Okay. Um. Okay. Let's go to this problem now. Before we solve this, rather, you answer this first. What do you think the answer is? Let's see what you remember from yesterday.
Um,
Okay.
RS,
RS.
change in pressure.
Okay. The answer is correct. RS. Okay. Let's do it like this. So remember, going up, pressure increases. So let's do it like this. So QR, pressure increases, volume no change, so no work done, right? So work done equals 0. Similarly for SP, let's just put it here. SP, the pressure is going down, the volume stays the same, so work done equals 0. Okay. Now what's happening in RS? Now let's use a different color here. Okay, so RS, oops, bad color. Let's do this, RS, and then let's look at QR. Okay, now in RS, what is happening here? The pressure is decreasing, pressure decreases, but volume increases, right? So because the volume increases, this is the important part here. So this means the work done is positive. Okay. Okay. Now similarly for QR, the volume decreases and the pressure increases. So again, we focus our attention on this. So this means that the work done is negative. Now, what does this mean in terms of normal English? Positive work done here means work done by gas. Okay, so the word here will be by the gas. Okay, now if the work done here is negative, then that means the work done is on the gas. Okay, so that's gonna be the difference there.
Okay, and why does the graph decrease not linearly?
Because in okay, let's take a look back here to the graph. I think here we go. Okay, now if you think about this, if the pressure stayed the same, then that's when you have isobaric the isobaric movement, right? Or isobaric conditions. Now here you can see that RS is doing this because this is either an adiabatic or an isothermal uh, change, okay, or operation. So what does this mean? Um, in either case, it's either there's no heat going into the system or coming out of the system, or there is no change in the temperature. That's all it means. Okay. Now, what
Um,
exactly is happening here, though? I think that's your question. What exactly is happening, right?
yeah, why is it curved?
Well, think about it this way: when the gas expands, let's assume one thing first. Let's assume that this is isothermal. Okay, so the temperature doesn't change, right? So when the temperature doesn't change, when the pressure increases, the volume must decrease, right?
Yeah.
Okay, so that's exactly what's happening here. If this were isothermal, that's exactly what's happening. When the pressure decreases, the volume increases, and the other way around. Okay, so that's if you assume it's isothermal, and most of the time, these would be isothermal, or let's say about not most, like about half the time for problems. Okay, now if we assume that this was adiabatic, so no energy comes in, no energy comes in, no energy goes out, right? So if this were adiabatic, then the PV and T things, all the pressure, the volume, and the temperature, they would kind of like interact in this really complicated manner, which makes it similar to the isothermal, but not as steep. But either way, that's gonna happen. Okay, so let's just write it here. So for adiabatic, uh, similar to isothermal, but not as fast. Not as fast. Okay. Oh, you say hi first
Yeah.
time. All right. Just a quick one. Say hi.
Hi.
Okay, bye. See you next year.
All right. Let's continue. All right. Any questions here?
Uh, that's okay.
All right. Um, let's make that calculator smaller here. All right. So, all right. Let's move on to the next question you have here. Oh, this one's kind of long. Okay.
Yeah.
All right. So the diagram below shows a variation with volume of the pressure of a fixed mass of an ideal gas. All right. The change from B to C is isothermal. So it's already mentioned this is isothermal at this temperature. At point A, the pressure is given. Point B, the volume. Point A, pressure and volumes are given, and the temperature is also given. Okay. So state the temperature of the gas at point C, and then calculate the volume at point C, and finally, let's just do that first. So how do you actually calculate these things, right?
Yeah.
Okay, so first of all, um, we will use a feature of this. Okay, so again, let's just do it like this. It kind of matters whether it's isochoric isothermal, or what was that? Choric, thermal, and baric, isobaric. Okay, we will skip the adiabatic process for now. Okay, so remember, isochoric means constant volume, right? Isothermal is constant temperature. And finally, isobaric is constant pressure. Okay. Now, here's the thing. For each of these conditions, there's an associated law, or there's an associated gas law, right? Even if you don't remember the names, we can actually just write it here. For constant volume, P1 over T1 should be equal to P2 over T2, right? Now, the second part, constant temperature, this is going to be P1 V1 equals P2 V2. And then finally, for the third one, constant pressure, we're going to have something similar to the first one. Pressure's constant. So V1 over T1 should be equal to V2 over T2. Okay. All right. So let's take a look now at A to B. This is where it becomes a little bit, well, actually not even. We don't need to go to B yet because we're only interested in point C. And you're given point A, right? So what is happening here? Let's just label this. A to B is isochoric. I'm just going to say IC. Okay? Isochoric. Okay? B to C is mentioned to be isothermal. So that's IT, right? Isothermal. So that means C to A is isobaric. So which one do we need for, we're given A, we want C, we're going to do the isobaric condition. So in other words, we're going to use that thing. V1 over T1 equals V2 over T2. Okay? So V1 over T1 equals V2 over T2. What's our volume here? Initial volume. Let's just put A and here, and let's put C here, right? So what's volume at A? Was it given? Yeah, at A the volume is 200 at 22.0 cubic. Okay, and then what's the temperature at A? 273 Kelvin. Okay, and for C, what's the volume at C? Is it given? Okay. Oh, okay. Actually, this is actually for part 2. Okay. Now let's do it here. There's gonna be a shorter way. Isn't for C, we know that's isothermal. From BC, it's isothermal. So the temperature doesn't change. So if the temperature at B is some value, then the temperature here should be the same. Okay.
Oh, okay.
All right. So we kind of overcomplicated that a bit, but we're on the way to calculate part C anyway. Part 2, right? So in this case, isothermal. So that means the temperature at B is equal to the temperature at C. So this means that temperature at C is equal to what is given. Did I miss anything? I think it's in the upper part.
546.
546. All right, there. Okay, 546 is over there. Okay, 546 Kelvin. Okay, then from here, to get part 2, we now have our formula. We're gonna put, let's go back to orange here. So this is gonna be volume over 546 Kelvin. We can already see that 546 is twice of 273. So from here, VC should be equal to twice. So 44.0 cubic meters. So no calculator needed, even though this is a calculator question. Okay?
Okay.
All right. change from B to C, this is the idea. Energy is transferred to the gas. Okay. And state the work done change from A to B. Okay, you already mentioned it. It's this. And
Yeah,
I think we've explained this yesterday very well, right? Okay. Determine the work done from C to A. Okay. This one's easy. The work done from C to A is work done is equal to the change in the pressure times the change in the volume, right? It's that easy.
yeah,
Okay, so we just put the values in. Um, we can already see what's the change in the volume here. So what's delta V? We know that the two volumes, one is twice the other, so it's going to be just equal to VA, right? So that's equal to 200 at 22.0 cubic meters. Okay. The pressure, we can get it from the graph or from the given information. The pressure here at this is 1.1 times 10 to the 5 pascals. 1.01 times 10 to the 5 pascal. Okay. And therefore, all we need to do is calculate that. So this is going to give us work done is equal to, put that in the calculator. This one is going to give us 22 times 1.01 is 22.22 times 10 to the 5. This is going to be already in joules. So that's going to be 2.22 times 10 to the 6 joules. Okay, that's the answer.
okay.
All right. Clear so far?
Yes, a lot simpler than I thought.
Okay, this is quantum mechanics. This is also quantum mechanics. All right. We have a lot of time. All right. So, okay, I'll just ask you first. Which ones do you want to go through here for these questions? So, like, which ones are you not sure what the answers are?
Um, all of them.
All of them. All right, no worries. So let's go to 6. Consider two photons A and B, twice the momentum. Okay, this one's easy. Number 6. Okay, because there is a formula in the booklet again which dictates the momentum of a photon. But the thing is, where did it go? Oh, here it is. Okay, greenhouse effects, gas laws. Let's go to quantum mechanics. That's gonna be D. No, it's gonna be E. All right. Uh, there we go. Um, not that, not that. Structure of the atom. Okay. Momentum. Is there? Oh, there we go. Okay. In the formula here in the data booklet is the wavelength. Okay. This is for any matter. This is for any matter wave or particle wave. Okay. The wavelength will be equal to the Planck constant over the momentum. So we can just rewrite this as the momentum is equal to the Planck constant over the wavelength, right? Okay. However, okay, let's see there. So we're gonna do momentum of A over momentum of B should be equal to 2. And that's gonna be H over A divided by H over lambda B. Okay, so from here, we're gonna focus on this part here. We're gonna get that that H cancels out, so 2 will be equal to um the wavelength of B divided by the wavelength of A. Okay, so we have this, and then before we continue looking at our choices, let's just write this down. This would be the opposite now, the frequency of A divided by the frequency of B. The reason why we do this, just so we're clear, is because C equals frequency times lambda, or in other words, the wavelength is equal to c over the frequency. Okay, so if we do the ratio, we're gonna switch these over again. Okay, so let's take a look here now. So what happens to the, well, let's take a look at the choices now. Photons don't have mass, right?
Yeah.
Okay, so that cannot be twice, because twice of 0 is just 0. So that's gonna be 0. So that's gonna be also 0. So that's false part, right? The frequency is twice as much. Let's take a look at what we did. Before that, let's go to D. They're both photons, so also incorrect for D because same speed, right? So we're now left with frequency or wavelength. So let's take a look here. Which one is happening? Which one is twice the other? So either, let's just rewrite this. So lambda B would be equal to lambda 2 times lambda A, or um, frequency of A is equal to 2 times the frequency of B. So which one is actually being described here? Which one is twice the other? It is going to be A. The wavelength of B, sorry, see, it's B. It should be B. Okay. What happens here? The wavelength, the frequency of A is twice the frequency of B. That's what we got. Okay. So that's why it's B. Okay. Clear?
Okay, yeah.
Okay. Now, the second part, the electron inside a hydrogen-like atom absorbs a photon of that much and jumps from the first to the second energy level. How much energy does the electron need to absorb the electron, to absorb in order to jump from the second to the third? Well, the answer is A, so you got that right. However, I'm assuming you don't know why that's the answer.
Yeah, I guessed.
Okay. Actually, this is the idea. There's actually a formula for this. But I think instead of discussing the formula, I'll discuss the idea. Okay. Hydrogen energy level formula. There. Okay. Formula. Okay. Now, quantum mechanics basically gives us this formula here. This is not. Is it in the data booklet? Let me double check. Oh yes, it's in the data booklet. I'll just show it to you. Okay. So it's this data booklet formula here for number 7. Okay. Now this formula basically comes from the fact that all atoms, hydrogen included, has energy levels, and the energy levels, you see that there's this negative sign here. Okay, the reason for that is if you recall, when we do energy levels like this, you notice that a lot of the time they're like not really progressing in any particular in any random manner. It's always going to be the biggest jump is from the first n equals 1 and to n equals 2. That's always the biggest jump, right? This
Yeah.
is the reason behind it. You see that there's an n squared value here. Okay, now if you want to solve for it, basically this 13.6 is for hydrogen itself, but for the problem it says it's a hydrogen like atom, right? So what we're going to do here for this particular problem is we're going to replace this 13.6 with 27. You get the idea? Why 20?
Sorry.
Okay,
Yeah.
I think you got lost there. So let me do that again, okay? So this 13.6 value is going to be the value for hydrogen itself. Okay? But
Yeah.
in our problem, it's hydrogen-like. It's not exactly hydrogen. So what we're going to do is we're going to replace that 13.6 with 27 to better describe our hypothetical atom here. Okay? So what does this mean? For n equals 1, the energy here, energy 1 will be negative 27. Okay? Now, to be specific, I'm going to have to write that as over 1 squared. Okay? this energy here on the second energy level will be equal to 27 over 2 squared. Or that's going to be divided by 4. Okay?
Yeah.
All right. And so on, so on, so on. Okay, that's one way to look at it. Now, another way to look at this is, I think the second way to look at it is slightly better. It jumps from the first to the second. Okay, it's gonna be better to think about it this way instead, because this is the more correct way of doing it. But basically, the idea here is that there's this certain value. Let's ignore that 27 for now. Okay, so from here to here, that's gonna be 27. Okay, so but you will notice that from here to here, the jump's gonna be smaller jump, right? And that's
Yeah.
exactly what the question is about. That jump from n to n, from n equals 2 to n equals 3. How much energy would that need? And from the diagram and from this equation, we can only say that the only possible value is a smaller value than before, 5 eV. Okay. Now B is the same, 27, but remember, we cannot have, because of this formula, it cannot be 27 as well. It has to be smaller than 27. So all these other values are eliminated just from that idea because of this equation. Okay.
But if we divide 27 by 3 squared, we would get 3.
Yeah. The idea here is actually that the energy at n equals 1 is not 27. It's going to be some value. Let's just say that the energy here is some value E1. Okay. And then the energy here is going to be some value E2. Okay. So if we do it properly with this formula, so E1 minus E2 is equal to 27. Okay. And this is going to be some value. This number will be some value x. So that's going to be x over 1 squared. Sorry, it should be the other way around. 2, 1 here. Yeah. X over 2 squared, but there's a negative here. Then minus negative x over 1 squared is equal to 27. So in other words, this is going to be 3x over, let's just multiply that by 2 and by 4. It's going to be 3x over 4 is equal to 27, and then we can calculate for x. But we don't need to do that. Okay? All we need to know is that this jump takes 27, and therefore, well, we can solve for x actually if we wanted to, right? So let's do that real quick. That's going to be, x will be 4 times 27 all over 3. That's going to be 9. It's going to be 36. Okay? So we now know that here, this is going to be negative 36 over 1. So negative 36, right? Then this will be negative 9. So what's going to be next? The third energy level, this is going to be negative 36 over 9. And that's going to give us minus 4. So from minus 9 to minus 4 gives us 5 electron volts. Okay? So that's the complete way to do it. The short way is, just remember, it just keeps decreasing every time you jump up. Each successful jump requires smaller and smaller energies. Okay?
Okay.
All right, great. So that's the long way. There's a short way. Both of them, I think, are clear. Let's go to number 8. We have an electron inside. Oh, sorry, that's the first one. No, that's another one. Hydrogen-like atom again. Okay. So a second electron with the same atom, within the same atom, has an angular momentum 2L. All right, let's take a look at the formula booklet again. Okay. Is it here? Apparently, it's not. Let me double check it. Angular momentum, conservation of angular momentum. This is your angular momentum. Okay, so this I'm gonna show you the formula in the booklet. It's not a straightforward formula. Okay, for number 8, let's do it on the right side here of the here. So here, this is the formula, but I'm gonna have to rewrite that a little bit. Okay, this is L. Okay, L here stands for the angular momentum, right? Okay, now this is gonna be the mass of the particle, that's the velocity of the particle, and that's the radius, that's the distance of the particle, or the radius of the circle of the path. Okay, N would be the energy level, H is still Planck's constant and over 2 pi. Okay, so basically for n equals 1, L will be equal to H over 2 pi. Okay, for sorry, not okay, and then for n equals 2, then that means L is equal to H 2H over 2 pi, or just H over pi, and so on. Okay, okay, so with that in mind, is there a relationship that, yeah, yeah, we kind of need the relationship here. The relationship is we're still gonna do that energy formula for the hydrogen like atom. Okay, so same idea. So we're gonna do the energy is equal to some number x all over a negative x all over n squared. Okay, so all right, so how does that work here? So all we have to do basically is look here. We're gonna compare the energy to the angular momentum, right? So if we look here, okay, so what's gonna be the L over E for now? That's going to be equal to N H over 2 pi divided by x over n squared, and that's gonna give us n cubed times times H all over 2 pi x. Okay, so that's the relationship, that's the ratio of L to E. So what we're gonna do now is what's gonna be so okay, or we can rewrite this to make it easier. That's gonna be L is equal to n cube H over 2 pi x times E, right? Now this is where it becomes easier. Now that we've set this up, all we're gonna do now is do L2 over L1. What's that gonna be equal to? So that's gonna be uh n here is 2, so 3, sorry, 2, so that's gonna be 8 H over 2 pi x times E2 divided by 1 is our n here, so it's gonna be H over 2 pi 2 pi x E1. What cancels out? This whole term cancels out. So L2 over L1 is equal to 8 E2 over E1. We now have our ratio. Let's take a look at our choices. So we're given that the angular momentums that L2 is twice L1. So that's going to be, so we're now gonna equate that to 2L over L, cancel out. So finally from here we get 8 E2 over E1 equals 2. Or finally E1 is equal to 4 E2. Okay, and there, let's take a look at our choices if 4 is there. Yes, it's going to be either A or D. Let's just be careful. The correct answer here would be, what is the energy of the second one? So what's E2, right? So E2 is 1/4 of E1. So the answer is D. Okay, so that's the long way. Let's do a, can we do a short way here? Not so much, I guess. All right, so let's go to 9. Any questions for number 8 there?
I understood it. Thank you.
All right, great. So let's go to This last one, a nucleus has a radius of 6 femtometers. What's the mass number? We're going to use this formula here. I'm just gonna write the formula here straight away for number 9. Okay, the formula here is R is equal to R0 A raised to 1/3. Okay, what is R0? R0 is a constant. It's the Fermi radius. Okay. Okay. So basically though, if let's take a look, there should be a value for that Fermi radius. Let's take a look in the data booklet again. Let's just make sure that it is in fact here. Content, math, fundamental constant. Fermi radius. There we go. Fermi radius is given in the data booklet. So here, all we have to do is just calculate that R. Sorry, A. A would be the, in this case, is the mass number. Okay, that's number of protons and neutrons. So in this case, that's going to just put the value in. So A raised to 1/3 will be equal to the R, 6 femtometers. R0 is 1.2 times 10 to the minus 15 meters. Okay, so we're going to just get that ratio from here. Femto is nano 12, 10 to the minus 12. Is it? Let's just make sure. Also, in case you've forgotten, it is also in the data booklet. The prefixes are there. Okay.
Right.
All right. Let's just see, where is femto. Femto is 10 to the 15. So this 10 to the minus 15 and the femto cancel out already, and this also cancels out. So we're left with A raised to 1/3. 1/3 should be equal to 6 over 1.2, and that's gonna be 5. 6 divided by 1.2 is 5. So from here, A is equal to 5 cubed, which is 125. Okay, so our answer is D. Now, that's the long way. But there is a short way for number 9. Look for a perfect cube. That's the answer. Okay.
Oh, what does it mean?
Well, 5 is not a perfect cube, right?
Yeah.
And neither is 6, nor 25. 125 is a perfect cube.
Right.
Why do we need a perfect
Okay.
cube? Because of the fact that we have that A raised to 1/3 is equal to some ratio, and it's gonna be a whole number. It should be a whole number. Okay.
Okay.
All right. So okay, let's take a look at the last question you sent over. Okay, determine the maximum energy when shines upon the plate. Electron. Okay.
The B is
B,
okay.
your B is okay from what I get, from what I gather. Yeah. Let's take a look at C. Calculate the wavelength of the electron emitted in B. So you've got this energy, right?
Yeah.
Sorry.
So
Okay.
I did some calculation, but
Yes.
maybe stupid question, but why is the wavelength not the same as the energy that it got it?
Oh, okay. Why is the wavelength different? Okay. So first of all, let's take a look here. That's the frequency, right? This let's label this first. This frequency here is the frequency of the photon, right? So this is the frequency of photon. Okay, and therefore from the frequency of the photon you get this, and let's label this again as the energy of the photon first, right? And then the idea here, this is transferred to the electron. Okay.
Yeah.
Now that you have transferred that energy into the electron, you're going to have to calculate it again to electron. Okay. So this electron energy, this new electron energy, you must find the frequency or the wavelength of the electron. Okay, is that what you've done here? The energy is correct, and this is okay. Let me see. I think there's a better formula to use. Let me double check. That's fields here. Planck constant equals mc squared and okay. Let's see. What formula did you use? Yes, it's gonna be different. Okay, here's gonna be the idea first. I think the formula here is you're supposed to use this. It's supposed to be the formula you use, right? Now, the reason why it's different, let's think about it this way. The photon has no mass. But to make it a bit easier to imagine, let's say it has a tiny mass. Okay? Let's just say it has a tiny mass. It's 0. But let's assume first that it's tiny. Okay? Especially when compared to the electron. The electron is also relatively tiny, but the photon, basically, because it's got no mass, it's like the photon is oscillating as it travels, right? So think of the photon as a pendulum. It's oscillating as it travels. Okay? Now that's a really good way to visualize it, isn't it? All right, anyway, going back. So as the pendulum or as the photon is vibrating, it's gonna hit the electron because the electron is much more massive compared to the photon. The electron's also gonna start vibrating, but not at the same frequency, right? So that's why the frequency between the frequency you got in the first one in B and the frequency you'll get in C are different, because B is the frequency of the photon and then C is the frequency of the electron. Okay, the energy will be the same. So that's the only thing that will be the same between the two, right?
And which one would have a higher frequency?
Since energy is okay, let's just put this here. That energy is, I'll just do it proportional to F, right? So that means since they have the same frequency, the same energy, okay, let's not do it like that because we're doing wavelength. They would have the same frequency, so to speak. Okay, but okay, there we go. Okay, what's gonna be the same? I think it's gonna be best to address it like this. Okay, if the photon is completely absorbed, then two things are conserved, and I think that's the problem. That's the thing here. The energy and the momentum are conserved. In other words, you need both. You need to find the energy of the photon, and that's what you got here. And at the same time, this is the idea. You need to find no, not the electron, but the photon's momentum as well. Okay, so the idea here is because it gets absorbed, so the photon and the energy are both, no, not the photon, the momentum and the energy are both absorbed, so the electron has the same momentum and energy. But now you're going to use that momentum to calculate the wavelength. Then from the wavelength, you calculate the frequency using the energy. Okay?
Okay.
All right.
Yeah.
Okay, so the last bit, D, calculate the work done on the metal plate, the work function of the metal plate. There is a formula for the work function. It's this. Let's just copy that. Okay. Here. So for the work function, this is the formula you use. Okay. Let's just explain this. This is still this is the energy of the photon. Okay. This is the work function. Okay. And this would be the maximum energy, the energy of the of the photoelectron. Okay, now the reason why we have this formula real quick is if we go back to energy levels, I think I'll draw the energy levels here. So energy levels, again, as we mentioned, the energy levels, the space between them gonna get smaller and smaller, right? So there's gonna be this final energy level. Let's say that the electron, because most of the time the electron, the photoelectron would be here. Okay, but sometimes the photoelectron is here, sometimes the photoelectron is here, sometimes it's here. So what's gonna happen is if you have several photons, they all have the same energy. Okay, they all have the same energy due to HF. Okay, now all of these, when they hit, let's say that this photon hits this particular electron, it's gonna escape, but it's gonna be, let's not use green, let's use green here. So this is gonna escape, but because it had to jump several energy levels, this is gonna have a low final energy. Okay, low final energy. Okay, however, if we have a photon hitting this particular electron like that, and it's gonna jump off like that, this will have a high final energy. Okay, and the reason for that is very simple. It doesn't have to really jump that much. So this electron here at the highest energy level, that's gonna have the maximum amount of energy right there. So that's why the formula has the word max in there. Okay, so having said that, how do you calculate this? Just put the values in the formula from before. So you know the frequency of the photon, you know Planck's constant, you know the energy of the electron, right?
Yeah.
So once you know the energy, you're gonna use this here. You're gonna use this maximum energy here, and then you can just work out the work function from here. So let's just do that. The work function should be equal to E max, sorry, HF minus E max. Okay, minus E max. Okay.
Okay.
All right. So from
Yeah.
there, we'll not solve it anymore. We'll just set the equation up. Okay.
Mhm.
Okay. Any questions? Any more questions here?
Everything's clear.
All right. Great. Okay. So we'll end here today. So I'll see you again on the next meeting. That according to this, it's on Thursday. Before we end, I want to confirm Thursday. You're all clear now, right?
I can't do Thursday.
Okay. So I'll have to reschedule them. Uh,
Could it the weekend maybe?
Weekend. All right. Can I do this just for this week or like the all lessons from now on?
I think all lessons is safer.
Yeah, I think so because you're gonna be really busy soon. When are your mocks?
Mocks are passed.
Oh, done.
Now it's real exams.
Yeah. All right. So yeah, I think we really need to move lessons. So yeah, I'll just move all the lessons to the weekend now. Okay.
Okay, thank you.
All right. I'll see you next week and have a good day. Bye bye now.
Have a good day. Bye bye.
All right. All right. So that's the end of that. And okay. Oh, I got a couple of chats from YouTube. Hi, but they were like a few hours ago. No, several minutes ago. So anyway, yeah, that's what happens when I'm busy here. I don't get the chats. I don't get to read the chats until we're done. So anyway, there we go. So yeah, yeah. So yesterday we did a few. We explained a lot of these, just to kind of get the idea. And now we've just finished going through the problems and see how to properly solve them. So for now, that's it. So before we go, don't forget to like, share, and subscribe to the channel. We are on Facebook, YouTube, TikTok, and Instagram, and we also go live on Twitch. So yeah, don't forget to do that. So with that, I will now have to say goodbye. So thank you for joining us on stream. So I wish you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.